Good morning, everyone. My name is Sachin, and today I'm presenting and submitting this assignment for my course CML661 Solid State Chemistry to Dr. Sajay P. Thomas. So, this particular assignment includes the synthesis, processing, and fabrication methods for the inorganic salts. So, without any further ado, I would like to start my presentation. So, we are going to study about the diversity of the inorganic solid forms, how they are synthesized, some common methods, and how to fabricate those. And the inorganic solids that we are interested in this particular assignments are the non-molecular ones. Non-molecular inorganic solid means that their motifs, the structural motifs are not the complex molecules, but simple ions. They are held to ions or atoms could be there. They're held together by the intermolecular forces of attraction. And these non-molecular solid form could exist in the fibrous form. We can make them in thin film form, plates form, powder form. Though they synthesis, the way that we can synthesize them is not an actually an issue, but the thing is, how do we them like how we form them into the fibrous material? How do we form them in the powder form? This is what is the major concern that we have. And there's one method that is known as the solid state reactions on shake and bake method. This is like solid state reactions in which both the reactants are in solid states. We are mixing the reactants that are in solid form rather than the gas phase reactions or the liquid phase reactions. This is one of the most like oldest and the simplest method in which we are going to take our reactants, going to mix them, and then we are going to heat them for the prolonged period. Here, as you can see this is one of the basic setup for this kind of reactions. We have our reactants in this particular crucible, and we are going to heat it in the one for at almost at a constant temperature, constant high temperature, for some hours, maybe some days as well. And using this method, we can make some superconductors. We are going to study one of such conductors which have like superconducting properties somewhere around 990 Kelvin. And there's one simple reaction that is in which MgO and Al2O3 they both are combining together and forming MgAl2O4, which are spinal structures. We are going to study about this in a little bit more detail after 2 or 3 slides. But the thing is that once there's a limitation to this solid state reaction mechanism. The particular limitation is that the reaction once it has started to like incur, once the reaction has initiated, but after some time it becomes slow, like it slows down. The reason is that the reaction is happening at the not at the atomic scale, but at the particles or the grain scale, and our product, our crystals are forming at the interface of our reactant. Let's say we have reactant A and B. Our nuclei of that particular crystal is going to form here. And after some time, as the reaction progresses, these two get separated. These two reactants get separated. But we have methods to like counter this particular limitation of this method. And the particle size that we are grinding in this are typically in the micrometer range. In the solid state reactions, we have the nucleation and some growth mechanism. And what is actually important for the particles to crystallize are the interface of the grains of our reactants. Typically, like ideally, we expect that let's say we have reactant A, B, and A. Like we expect them to be homogeneous in nature. Like they are like widespread, but they are like an almost equal composition of their particular compound. And at their interfaces, we will start to see our crystals. But the thing is, the crystals that are forming here, this crystal formation are called nucleation. But these nuclei that we're getting, they should be of a particular threshold size. If they are going to be like of smaller size, then their positive surface energy is going to be very, very high, and they are going to be unstable. So their their size should be of a particular threshold size. The so that they can overcome this nucleation barrier. And we know that this reaction is taking place at a high temperature, so they, of course they require high thermal energy because to clusters to form, right? Now, there's one more thing, homogeneous nucleation. What does it means that we had our one grain A here, it could have many crystallites in it, and B grain here. So at their boundaries, we are going to form our product. And this product should be of different phase or different type of crystal structures and could be totally different from our A and B reactants. Like in the case of MgO and Al2O3 plus reaction and forming the MgAl2O4 spinels, they all have different kind of structures and different kind of properties. So this is what heterogeneous nucleation actually means. Nucleation is generally facilitated if it occurs on the surface of existing structure. Let's say we have MgO, and at its surface we are going to form the spinels, the MgCCP, and spinels are also CPCP, but they have different composition of ions, and the location of ions are also very different. We are going to study about the MgAl2O3 and Al2O4 in a bit more detail. And there has to be some structural similarity so that we can have some coherence between the product and the reactants. We are going to talk about all these terms in details. Don't worry about all this. But few things that from this particular side that we have to learn. First thing, your nuclei that are forming at the interface should have a size equals to or greater than the threshold size so that it can be stable. And the heterogeneous nucleation can occur at the surface because the product are in the different phase or different type than our reactants. Huh. These are the few things that we have to keep in mind. First thing, the other structural matching actually, like structural matching between of the product and the reactant. First thing is epitaxy, means there's a structural similarity between the product and either of our reactant at the 2D level. At the 2D level, on the surface, both of the surface may look same. So epitaxy is mostly seen between in Al2O3, Al2O3 SCP structure and our spinal MgAl2O4 CCP structure. So there's only the surface, 2D surface are in common, but topotaxy occurs when there is a similarity between the ions packing in the 3D structures, which occurs between the MgO-CCP and the spinels that we are getting in CCP. Oxygen atoms are present at the face center and at the corner. And coherence means that the distance there should be good lattice matching between the reactant species and the product species. For example, in the MgO, the spacing between the oxygen is kind of comparable with the oxygen distance in our spinals. So this is known as coherence. Now there's one more important phenomena that is known as the counter diffusion. Like what is it actually? So as we have studied in a little bit earlier, that the product starts to form at the interface, right? I'm drawing this interface a little bit far away, but let's say we have product formation here. So due to the product formation here, our reactants are not that much accessible to each other. They are not that much in the close proximity that they can form the products any further. So what we need a process, right? We have to somehow mix them together. So what we can do, either we can stir them manually so that they can come in close contact with each other, and one more thing is that when we stir them, like we are hitting them, so our Mg2 positive and the Al3 positive ions, they are actually moving towards each other because all of these reactions are happening in the molten phase, not in the solid phase. Now, because they're occurring at the hundreds and thousands of degrees Celsius, so there occurs the diffusion of ions, like from MgO, Mg2 positive also diffusing towards the Al3 positive, and together they are forming the spinels. So counter diffusion, once a layer forms, reaction slows, right? Once our product reaction layer has formed, reaction starts to get slowed down. But for the further growth of the ions, we need ions to come close together, right? And this movement of ions to after the first layer has formed towards each other is actually what gives rise to counter diffusion. This particular image actually represents what counter diffusion is actually all about. This is the product layer that we have gotten, right? Now our Mg2 positive and Al2O3 and giving Al3 positive and the Mg2 positive. They're not accessible, but then the molten state reactions and at the interface, what happens actually? The Mg2 positive ion starts to move towards the right side, towards the product side, and also our Al2O3 starts to move to the product side. They come to the surface or maybe somewhat got diffused into the products, and they form at the interfaces. I'm talking about at the interfaces. They starts to form the products again. We need ions movement. If they would have been solid only, then they won't have any ions movement. This is happening because there's a high thermal energy between the ions and they are in the molten state reactions. We were talking about coherence, the structural coherence, right? So this is our MgO, which has CCP structure, Mg is positive present in the octahedral voids and the oxygen at the FCC lattice. Same goes with the spinels. In Mg is present in 1/8 of the tetrahedral void, and the octahedral voids, 2/4 of the octahedral voids are occupied by the aluminium. But our oxygen is still present in the FCC here as well. All of these two have like ABC, ABC kind of close packing, ABC, ABC kind of close packing. But the case is a little bit different when it comes to the Al2O3. In the Al2O3, there is a AB type of close packing because it occurs in the SCP structure. But the oxygen are closely packed together, both in the SCP of the Al2O3 and the spinel that we are getting. Yes. So there are two interfaces that we are getting, right? There are two interfaces because one of our reactant is MgO and the another reactant is Al2O3, and at their surface the reactions are taking place. This is where the product starts to form. So at the interface of MgO and MgAl2O4, because we are talking about this particular interface here, and this particular interface we're going to talk about here. So here, Uh, for every two Al3 positive ions, we have three Mg2 positive ions, and MgO is present because it's one of the reactant, and these are from the counter diffusion of ions, and we are going to form the products at the interface. Similarly, at the right side interfaces, our three Mg2 positive ions are going to migrate toward the interface. There are going to be present some two Al3 positive ions at this interface, and Al2O3 is also present at the interface, and together they are going to form three molecules, three equivalents of the product spinels. And the overall reaction could be written here as like there are four MgO positive, four MgO, sorry, and four Al2O3. Together they are forming four MgAl2O4 structures, spinels. So there could be a special effect that we can see. It's known as the Kirkendall effect. Kirkendall effect. So what is this effect about is, let's say we have a reactant A and reactant B, and they are of the different reactant A and B could be of different, could be of same color, but the product that they are forming is of very different color than our both of reactants. So as this starts to come in contact, the product is going to start to form. We can see the diffusion of ions and the product formation, but for that we have to plan the reactions accordingly. Some particular case study about the solid state reactions we are going to cover in this particular assignment. One of that is the Li4SiO4 synthesis. So there are some challenges that this is a reaction for this particular synthesis. There is allied lithium carbonate and silicon oxide, silicon dioxide heated at the 400 degrees Celsius for 24 hours, giving us the Li4SiO4, the product of interest, and as CO2 is going to like we are going to desiccate it. It's going to like out of the product, and like we can get the porous material and we can break it down to powder form. The main challenge is that the Li2CO3, the starting material, it melts and starts to decompose at 720 degrees Celsius, and it is highly reactive with the container that we are using, reaction container, platinum or silica glass. So to mitigate this particular limitation or challenges, what are we doing? Actually, we are using copper container, and we are going to preheat this particular reactant, lithium carbonate, at 630 degrees Celsius so that it doesn't react with the metal container over our, and then we are going to process it for the like prolonged heating for the overnight heating, like for the 24 hours we are doing this reaction. So we are going to first preheat the solution and to initially partially or maybe partially we are going to complete this reaction and then we are going to keep it overnight. Then we are going to, there's one more method, one more particular class of compound known as the YBCO. They are the superconductors at 80 Kelvin that we talked about in the starting of the PPT. And they, the reaction for the YBCO compounds is that we are going to get yttrium oxide, barium carbonate, copper oxide, and we are going to heat the for like at a high temperature, but at the two different temperature we are using. There's a reason we are using two different temperature. We are going to study about that as well. So when we were like making the YBCO superconductors, the barium carbonate like it's very difficult to decompose because it doesn't get decomposed completely, and copper oxide also starts to react with the container as well, and we have to maintain the content of oxygen in the reaction because superconductors has to be of high purity so that we can control their TC, that is a critical temperature. So what we found, like how to resolve all this problem is that we have to plan out this reaction in a CO2 free environment. We have to use a different kind of atmosphere or different kind of starting material. So we use barium nitrate, we're going to hit it and we're going to get barium carbonate. Instead of barium carbonate, we are going to get the nitrate because if it's going to decompose, it's going to form not going to form CO2. And we are you're also going to use a prepared bed of IBCO so that we can crystallize over the particular bed. It's like seeding the particular crystallization. Like during the crystallization, we use nucleation and seeding, right, from external sources. And this is like that only. So we are using pre-made bed of IBCO. And final heating at the 300 degrees Celsius for the uptake of oxygen because we need oxygen in this particular reaction. Then we are going to heat it overnight at 950 degree Kelvin, 950 degrees Celsius, sorry. For the solid state reaction, there are so many things that we have to keep in mind before we perform any solid state reactions because they are typical class of reactions. The starting material that we are using should be of high purity. They should be stable, but should be reactive as well. They should not be inert, and they should also not react with the container. The mixing method that we can use, we can do manual mixing like mortar and pestle kind of. We can use mechanical mill, bowl milling we usually call them, and the container in which we are going to heat our reactants are going to mix them together. It We can use different kind of container. We can use copper container, aluminium oxide, silicon oxide, quartz, platinum, but different graphite as well. But the container should be chosen in such a way that none of our reactants should react with it. It should be inert and should not introduce any kind of impurities to a product as well. Then the firing schedule. Firing schedule is typically about for how long are we going to heat our particular reaction mixture and how we are going to heat it. We have to design it such a way that the product doesn't degrade, doesn't volatilize that much, doesn't react that much with the other atmospheric environment, we can say. Now, other than the solid state reaction, we have another class of reaction, also known as combustion synthesis or explosive chemistry, because in this class of reactions, class of preparation, we are going to reach a very high temperature, much more high temperature than what we have used for our solid state reactions. One of such class of reactions are SHS. They are known as the self-propagating high temperature synthesis. In this reaction, we are going to initiate the reaction at a high temperatures. Like by sparking the reaction auto-propagates. Like in the solid state reaction, that usually takes like days to complete. In this method, we can complete those reactions in like seconds and even in minutes. In this The basis of this reaction is that the starting materials reacts very exothermically. Like once we have sparked those reactions, it reacts very exothermically. I mean, on the heat that we get out of the exothermia, it is used to like propagate the reaction. One of the classic example of this kind of reaction is thermite that is used for the in the railway line. Once we have to weld the railway line together, now there is some breakage on the rail tracks. So we use thermite to infuse those together, to melt those together, because thermite can be used to reach temperature somewhere around 3000 degrees Celsius. The reaction for the thermite is Fe2O3, and aluminum we are using, we are then it's got Fe2O3 gets reduced to Fe, and aluminum gets oxidized to Al2O3. And the temperature that is achieved during this reaction is 300 Kelvin, 300 degrees Celsius, sorry about that. And the time scale, the reaction could be completed within like 30 seconds. And using these reactions, another spinal compound of nickel, zinc, and iron could be made. Now, there is one more class of reaction. There's one more class of reaction that also falls under this explosive kind of synthesis, known as SSM, self-sustaining metathesis reaction. In the last reaction, the driving force was the highly exothermic reactions, but in this case, the driving force is the lattice energy of the side product. We are going to get a one main product and one side product, and the lattice energy of our side product is what perpetuates the reaction. And the control, what actually controls the rate of the reaction, the temperature that we are going to get. It is the limiting factor is the boiling point of our side product, because as our side products start to degrade, so does our rate of reaction starts to deplete. So we basically just mix our reactant compound, and the compounds are very highly reactive. They start to react, and we are going to form our side product. And with the lattice energy of side product is what facilitates this reaction. So one such example that is based on SSM is that this we want to make tantalum nitride. The starting material is a lithium nitride, and we are going to react it with the tantalum chloride. So lithium chloride is our side product, whose lattice energy that we have used to make our product of interest, which is tantalum nitride. Now, these reactions have found their uses in making the carbon nanomaterial carbon nanotubes. On one such reaction that depicts its uses, we are reacting the lithium carbide with the carbon halide, and we're going to get carbon nanotubes. And carbon nanotubes are like like very strange and like very strong material. They have like applications in the modern sense. There's also one more class of reaction that we are using. It is another mechanosynthesis. As the name suggests, it has some mechanical issues, so not issues, mechanical forces. By using some mechanical method, mechanical forces, we are synthesizing something. Means it's nothing. We are just going to get our reactants. We're not going to heat them. We are going to just grind them together using ball mill, and we are going to get a product. The thing is that we are going to grind them so hardly that at the localized point, at the grinding points, they're going to achieve some high energy, and they are going to infuse together. They're going to react with each other and giving us product. The unique feature of this reaction is that we are not hitting them, and the product that we are getting may be completely different from the product that we will get once we have heated the reactants together. We, this is one of the particular like enigma of these kind of reactions. Other than the solid state reactions, we have another kind of methods to prepare the inorganic solids. They are the chemi method, or also known as the soft chemistry methods. In the previous class of reactions, the reactions are taking place at the particle level or the grains level. But in this case, they are reacting at the atomistic level. So one reaction and one process that falls under this umbrella term is a sol gel process. As the name suggests, there is some solution involved, some gel involved. So what are those about? We are going to get our metal alkoxides. We're going to mix them together in a solution. The first part of the reaction is completed. Then we are going to hydrolyze them. Like the alkoxide could be converted into alkoxides. Alkoxides are going to convert into the alcohols, maybe acids as well. Then we are going to condense them together by removing the water. And this is when the solution has converted to gel. Then we are going to condense our gel. We're going to heat our gel to purify and to crystallize our solids actually. To remove the volatile substances, we have to heat it. This process is calcination, by the way. We have to provide heat to remove the any organic impurities, sustained volatilities. So one such example showing the hydrolysis of silicon alkoxides. We're going to hydrolyze them, and the OR group has been replaced by the OH group, and so on. The second part that involves the condensation in which two of the processed and the hydrolyzed alkoxides they fuse together and form the gel. They are going to form the gel matrix actually. A simple condensation reaction, this S2 is going to get removed from here. Using the sol gel method, we can also form spinels actually. But the thing is that the typical method that we use for the formation spinel, the solid state reaction, it has to be done under very, very high conditions. And the alkoxides that we're using, like magnesium oxide, aluminium, we were using Al2O3 and MgO. They're like very easy to procure, inexpensive reactants, right? But the only limitation was the temperature was so high. Like, but it was cost effective, by the way. But in these reactions, they are not cost effective at all because the reactants that we are using, they were very niche. These reactions are carried out at a low temperature. That's one of the important key features of them that they are not that much energy demanding in comparison to the solid state reactions. Like one such example that is used for the formation of spinels, this particular spinel, AMG Al2O4, we are going to use this magnesium methoxide and aluminum butoxide reactants, and we're going to heat them together. They're going to mix them in a particular solvent. Then we are going to heat it. Once the solution has got converted to the gel or like heating, and then we're going to evaporate that gel and we're going to process the gel for the purification and other processes. And at the end, we are going to get some fine particles formation. There's a indium tin oxide that could be formed by using this method as well. ITO has like some particular applications in the semiconducting industries. They are using the electrodes and in the light emitting diodes as well. And using the gel process as well, we can make indium and tin alkoxide. Indium and tin alkoxide it could be used to form like very thin plates of material, amorphous materials as well. Indium dioxide, now they actually transmit the visible lights and reflect the IR lights. Then there's also some other examples like tantalum pentoxide on the silicon, making the coating of those people, those substances. Like till now we have studied, like we can get the spinels in the form of plates, in the form of network, in the form of solid cube, no, not cube, like 3D morph actually. But we can get the plate out of them. We can make a thin coating, which could have some applications to our interest, like the silicon oxide and titanium oxide on the silica. If you're going to do it like this, where silica is our semiconductor, if you're using solar cell, and this is coated with these two moieties, these two particular inorganic compounds, they have the anti-reflective properties, means they will not reflect that much sunlight and help the silicon to absorb as much solar light as possible. And this particle oxide is used as an insulator for the capacitors we use. The thing is that thing with the coating and making the thin film and sheet is that there's a chance of non-uniformity, non-homogeneity, and crackling as well. We have to keep all this into mind. Now, there's also one more important class of substances, zeolites. If you all have heard zeolites, if we are into solid state chemistry, we know the zeolites are the MOF, which are the competitor of the zeolites. Zeolites are nothing but aluminum silicate framework, which have avoidant cavities that could be used for the ion exchange, for the catalysis, and other purposes as well. So what we are doing to do, these kinds of synthesis are actually fall under the hydrothermal kind of synthesis. So what we are going to do, we are going to mix these reactants together and then at the high temperature and pressure, we are going to heat it. And we have like sodium aluminum hydroxide, sodium silicon oxides, and NaOH. And then we're going to use them together and I'm going to heat them at the high pressure. And as a control, as a template control, we are going to use ammonium. We are going to use ammonium, alkyl ammonium, you can say. This particular moiety we are going to use for the template. Uh, wha- what are templates actually? Template actually provides the structural basis for the zeolites to form. They like the bed, they like the blueprint. Okay, so they're like the blueprint. So how would I explain the templates? Templates are like the blueprint. Like on the basis of the template, we are going to form the let's say this is our template. On the basis of this template, we are going to form the zeolites that have cavities. The size of these cavities actually defined by the templates, and the template that we're using are these. The arc group, when depending on the arc group, we can like tune our voids and the cavities in our zeolites. And the thing is that once the reaction has completed, what we are going to do is we are going to boil it off. We're going to heat off the this temperature. Temperature starts to degrade somewhere around 300 to 400 Kelvin, and once it has gone away, we are left with our zeolite only. Hydrothermal synthesis method, as the name suggests, we are using hydro means water and heat for the synthesis process. So we are going to use the material, we are going to heat the reactants in water at the high pressure. And the water here acts as both as the solvent and as a pressure media as well. Because water at the high pressure, of course, going to insert some pressure onto the reactants. And there's one thing that we have to keep in mind is the supercritical temperature, supercritical state of our water. This 374 degrees Celsius means our water here existing both as the liquid and both as the steam. So what we are doing is actually we are taking our reactants in a particular chamber. Let's say we have reactants here and we are going to shoot it with the water like very, very high pressure. And they're going to come together, they're going to press it together and the substance start to react. I'm going to get the product. That's the basic principle behind it. And the chamber into which this reaction is taking place are known as the bomb actually. The next step, they're known as the hydrothermal bombs. They have the application in the geolite. So in the geolite, what we are actually doing is we are taking these reactants, we are mixing them together, then we are processing them under the high temperature and pressure. Another method that is used that has application is the Bayes method. Like this method, hydrothermal synthesis method, could be used for extraction of aluminium, which is an ore. Alumina, which is an ore of aluminium. Aluminium oxide, yeah, bauxite, is got bauxite is the naturally occurring ore of aluminium. From the bauxite, we make Al2O3. We are going to process it, removing all the impurities. And from Al2O3, we are getting the pure aluminium. So we are going to study about this in a little bit more detail, the BS process. This is the industrial process for the processing the ore of aluminium to get the pure aluminium. As simple as that. This one particular graph is important actually to like understand this hydrothermal process of like making the solids. This is the temperature versus pressure plot that we are getting, and this dotted line actually what are they representing? They are representing the number, the vessel that we are using, hydrothermal bomb. What percentage of it is filled with the water, right? And the volume is kept constant. At the if like if it is filled 90%, at the temperature increases, the pressure is just around 2 kilobar. And similar to this, and this line, the curved line, this point, this B point actually represents the 374 degree Celsius, the supercritical point. This is the typical diagram of a hydrothermal bomb. We have the starting material. Let's say we are making zeolites, yeah, we are making Al2O3. We are going to put it here. This is the hotter end because this is we are heating it. Then we are going to subjugate it with the high pressure water, and this is the cooler end. As the we are basically creating a temperature gradient. Uh, Here the solubility of the product starting with it starts to increase. They infuse together as the temperature lowers. This is where the nucleation of the crystal starts. Base process is what? This is used for the making the processing of bauxite ore. This is the bauxite ore, impure Al2O3. We're going to crush it, we're going to mill it, then we're going to mix it with the NaOH, we're going to subjugate it to high pressure, high temperature. We are going to get this gibbsite. From the gibbsite, this is gibbsite. From gibbsite, we are going to hit it again in the rotary kiln and we're going to get the pure alpha Al2O3. And using the hydrothermal processes, we can also make quartz, like single crystal quartz, like SiO2, we can be using hydrothermal processes. Same, we are using the hydrothermal bomb and we are creating a temperature gradient at the hot end. At the hot end, this hot end, our SiO2 reactants, they dissolve, the solubility increases, and as the temperature lowers here, let's say there's a lower temperature, here the supersaturated solution starts to form the SiO2 crystals. SiO2 crystal starts to form here. And at the end of my PPT, I'd like to compare all those methods that I have covered in this. First method, that was the solid state reaction shake and bake method. Temperature, it is like very temperature dependent, very high temperature. Reactions are taking place at the particulate level. Very simple method, proven like for the ceramics and all that. Then as such, that is combustion method, right? Temperature is very high, like hundreds and thousands of Kelvin. The reacting species are reacting at the atomistic level, not at the atomistic level, particulate level actually. Extremely rapid, like thermite reaction that we just studied in this one. This reaction we have studied the MgO plus Al2O reaction. Then salt gel method we are using, temperature initially is very low, right? Then reactions are taking place at the atomic level. We are getting the gel, and then we are heating it to purify it. Then hydrothermal we are using at the moderate temperature but very high pressure we are using. The reactions are solution phase reactions, and the single crystals of SiO2 or zeolite could be formed using these reactions. Thank you everyone for listening to me. This was me. This was for my assignment CML661. It was a bit new topic, bit interesting. Had less time to prepare for it. So yeah, I wish you all very good luck. Have